Hello, this video clip is about to explain general topics in week number 7 of ele361 Electrical Machinery 1 course. So we'll go through our usual slides to contain information about stored and converted energy in magnetic materials. Now, magnetic stored energy in a magnetic circuit like the one as shown on the right side of the figure, containing one coil and one magnetic loop. That loop may or may not contain the air gap. Here, the air gap is shown, and the change in the energy shown as the delta W is generally, in terms of the power and time variation, the integration from time one limits T1 to T2 of the total power integrated through the time domain. So if you converted the power to voltage and current, that voltage is specifically the induced voltage shown with lowercase e. P equals to EI, and that E is the induced or the flux, time variation of the induced flux multiplied by the number of turns of capital N, or the flux linkage, time derivative of the flux linkage d lambda or dt. So the integral becomes underneath an enclosed rectangular box as delta omega equals to, from lambda 1 to lambda 2, I multiplied by d lambda. So that's generally the integral. When the relationship between the magnetic field intensity and the magnetic flux density, so that integral is just the area under the triangle between the curve to the vertical axis, okay? As shown is as that blue shaded area under the graph, okay? The shaded area is related to the energy. So energy is basically defined as the area between the curve, BH curve, or equivalently lambda versus I curve from two extreme points, from the initial point to the final point, okay? So everything can be converted. Lambda can be converted to flux. Lambda is the flux linkage, or flux can be converted to magnetic flux density B. Similarly, I can be converted to MMF, or MMF can be converted to H. So the curve shape will not change, only the units and the amounts will change, okay? So the change as written from our general formula of delta W, or change in energy, equals to the integral from lambda 1 to lambda 2 ID lambda, represents the change in energy of the system by increasing the current from one value to another. So the current is in the horizontal axis, and corresponding lambdas are dependent variables in the vertical axis. When everything is linear, as shown underneath, change in energy is 1 or 2L, and the difference of the squares of the lambdas. So it's very similar to the change in inductor energy stored in the inductor. If the initial condition is 0, where the I1 or lambda 1 is 0, it's the same as the stored energy in a general inductor. When we consider the general case from any value, from phi1 to phi2, as shown in the nonlinear graphics. Okay, these nonlinear graphics are very typical to our magnetic circuits in this course, electrical machinery course. So the same equation So beginning from the top of the slide, delta W equals to integration from lambda 1 to lambda 2 times the current, which is the function of the flux linkage, integrated with respect to flux, can be transformed to lower delta W with different integration limits and different variables, integration variables. So lambda 1 can be transformed to phi 1 by dividing it to number of turns of the coil, which is a constant value. And I can be converted to MMF. Again, it's a division of a number of turns. And d lambda can be transformed to d phi, again with the same proportional to ratio of the number of turns of n. So before dealing with the general energy equations, we have to keep in mind that in the first case, we assume idealistic conditions where there's no loss, mu's are infinite, etc. But in real life, energy is lost in all physical systems. So what kind of losses do we have in magnetic materials? One of them is eddy current loss. So if we have a conductor, like a wire or copper wire, any conductor, and this conductor is in the vicinity of alternating current or time varying change uh, in this conductor results in induced voltages. Induced voltages result in circular induced currents. Induced currents in any physical material means that it's flowing in a resistive path which has power loss. So underneath, there's a kind of general formula for with some proportional to constants related to voltages, magnetic flux densities, and some geometrical constants, etc. And this power loss is proportional to the square of the frequency. So if we increase the frequency, we increase the eddy current loss in general. The second type of loss is called hysteresis loss. Hysteresis, as you remember, one of the main properties of the loss in the transformers because of the ferromagnetic materials nonlinear behavior. And that nonlinearity also shows hysteresis characteristics, meaning that if we increase the current to some value, to some maximum value, and then return back to zero, then the magnetic flux density does not follow the same path. So there's a kind of two-way path of circulating magnetic flux density in a material, which results in given magnetic field energy. Note that the magnetic energy is the area between the nonlinear curve and the vertical axis. If two paths of magnetic flux density curves follow different paths, then the areas are different. So in this area, okay, as I told, if you apply a sinusoidal wave or any waveform with a periodic cycle characteristics, like the one shown on the right side, when we increase from zero state to some maximum value from point O, specifically on the waveform from point K, which is the peak value, on the left side, on the hysteresis curve, it starts from origin and reaches to maximum B, maximum H value of K. And if the cycle returns back to its zero to the point L, so positive cycle and starts from zero on the graph, reaches to peak value point K, and diminishes to value L, that L value on the hysteresis curve is not the origin. Okay, so that's the hysteresis characteristics. And the area under the curve of these two paths with uh, the vertical axis, magnetic flux density axis, then meaning that I give energy, but the system returns me less energy. That less energy or the difference energy is the shaded region per cycle. Okay, so if I have um, a 50 hertz, then 50 times of this energy is lost in per second. And let's refresh everything. So these two mechanisms are the eddy current loss and the hysteresis loss are observed in magnetic circuits. And eddy current loss is also incorporated in the Maxwell's equation, combining the electric field and the magnetic fields. Okay, the divergence of the electrical field is or equals to the time derivative of the change of the magnetic flux density. That minus sign is just for opposing that change. Question may arise in our mind. Can we say that eddy current originates from hysteresis loss? Because hysteresis loss is an abstract concept. That was a student question in my former years, thanks to that person to contribute my course. The answer is straightforward. Hysteresis phenomena comes from electronic and magnetic properties of ferromagnetic materials, coming from the elemental or atomic structure or spin numbers of the electrons in the outer shell, whatever the quantum concept you can accept. Thus, it's related to the electromagnetic spins and ferromagnetic atom, and it's in its crystal environment. On the contrary, the current losses occur due to free charge circulation inside the solid ferromagnetic material. So those are outside the atom, freely available in metal structures. Okay. So in any case, always consider the basics and add the units in your discussions or supportive statements. So these two things, hysteresis and eddy current losses, contribute to total so-called core loss of the material. So let's come back to idealized electromechanical energy conversion. And after that, we will add these loss mechanisms as well. But fortunately, total losses usually count less than 5 or 10% of the general power rating of the material if it's designed in a proper way. So electrical machines transfer power and or energy between electrical systems and mechanical systems. Electrical systems do carry voltage and current. Mechanical systems do carry force, torque, displacement, etc. So those are some kind of mechanical structures to rotate by means of some outer physical force or mechanical power actuators like water, falling water or some kind of fuel-powered engine, or even if human power as well. So this is the schematic representation of electrical mechanical energy conversion device. At the left side, with so-called yellow box, there's an electrical system supplying voltage and current towards right over some kind of transmission line with having a resistive component, or can be modeled as a single resistor. And in the middle, pink, box represents the coupling device. So electrical current is coupled as a magnetic field energy. And this according to the geometrical design of the stuff, yield some mechanical action like rotation or linear transformation. So, in the first equation with yellow encirclement, change in the electrical energy results in change in the electrical power loss minus some loss component due to that copper losses or transmission line losses. And under all the equations, this is derived as if we change the electrical energy, we change the mechanical energy as well as the stored field energy. So change in the electrical energy will result in the addition of two changes in the mechanical and magnetic energy. So this diagram also has voltage and current polarities and directions or sign conventions. So whenever some device, if the current is flowing out the positive terminal of the voltage, that's a kind of power generator form. So it generates power. If any device receives current into it from the positive terminal, that's a passive device which consumes power, or power is delivered to this device, okay? So that's a kind of refreshment to our circuit theory conventions. So considering the first or left part of the energy conversion device from electrical system to the coupling device, which is a magnetic circuit, okay? Change in the electrical energy, if you remove the loss components in copper losses, I square R losses in the wires, just converted to the magnetic systems induced voltage times current type of power, or in energy terms on the right side, as you see, E times I times dt. So E is induced voltage, I is the current entering to the system, dt is the differential time to calculate the total energy of the coupling device. So that's a simple one mesh circuit, which is typical for electrical machines. Next question, because we will investigate the first very basic electrical machine of moving plunger in a simple electric circuit. So why electromagnets attract ferromagnetic materials? So that plunger, as you see, contains two parts in its magnetic circuit. One part is letter C type and the other one is letter I type. And this I type is a moving plunger, so its air gap can be varied. So in two extremes, it's widely or fully open with largest air gap, and it's fully closed with almost zero. Zero air gap is not possible. That means the energy density is infinity. Ideally, it's not possible. Because all physical systems tend to minimize their total energy in the nature. Electrons fall in the lowest energy vacancies. Mountains try to be flat on the earth. Gravitational force attracts everything to minimize the potential energy on the earth. Or similar, finally, our concern, electromagnetic circuits tend to minimize stored energy. That's the reason moving plungers are always attracted to minimize the reluctance, to minimize the source. So this is the general model for electrical excitation. In the circuit you see on the left side, there's an electrical excitation or electrical source and a coil with some inner resistance. That coil creates magnetic flux, and this also creates magnetic fields in the moving plungers. Plunger is left, or the moving part of the plunger is attracted towards left side to close the circuit, magnetic circuit. So closing magnetic flux means, closing magnetic plunger means its mechanical energy changes because there's a force, there's a linear displacement, they are in the same direction or in the reverse direction, no problem, because that makes either creates or delivers mechanical energy. So change in mechanical energy occurs, and this equals to the force times delta x. So force times dx is the work done of the system. The conventions, if that is a negative, has a negative sign, that power has a positive sign, that's the power is delivered to the load. If it's negative, that's the power is generated. So but the magnitude does not change. Only the sign determines whether there's a source or power source or power generator, power load. Okay. So underneath the blue statement says that if it's greater than zero, then electrical system does work on the armature. And in the other case, the reverse, mechanical system does work. So our ferromagnetic system has nonlinear MMF, flux versus MMF characteristics as shown. As I said in the beginning of the lecture, this video, the energy is the area between the curve and the vertical axis. So the other area, so between the curve and the horizontal axis, is called co-energy. So co-energy is like complementary energy. Actually, it does not represent a physical quantity. It's just a mathematical notation to give a name of its complementary. We will see that in this slide series. We will see that sometimes calculation of the mechanical force by using that co-energy is simpler. That's the reason it's used. Basically, co-energy is shown with a prime sign, W field prime equals to the total area of the square, the maximum MMF F1 and maximum flux phi1 is multiplied and energy is subtracted. So addition of energy and co-energy is F1 phi1. So if we return back to our plunger example, so what's happening in two cases when there is big air gap or maximum air gap and zero air gap? There are two different conditions. These two conditions do have different magnetic field reluctances. And these reluctances or the magnetic circuit changes, and since the air gap length is different and reluctance are different, so its magnetic characteristics are different. So they are shown in the upper left part. There are 2 points, zero air gap and maximum air gap condition with different magnetic flux densities and different MMFs. So we can define theoretically, if we analyze in a simpler way, we can either model mechanical movement of the plunger by so-called slow motion. So in the slow motion, the MMF is assumed to be constant. In real life, it does not. In real life, there's a complex relationship between the MMF and the flux. So both of them interact together and act or change accordingly. But if you model them in the simplest case, we either can assume constant MMF, you see on the areas on the top of the curve, okay, MMF is changing from point A to C in a constant way. Only flux changes with the constant MMF. So the shaded area underneath, that blue area, represents the change in the mechanical energy to the system. So moving the plunger in two different magnetic circuits with maximum air gap and zero air gap. Conversely, so if you look at the characteristics, from in the initial situation, MMF is zero and it's constant, and flux is phi zero, which is the lower phi in the vertical axis. So stored energy is A2 plus A4 in the first case with the blue outline condition. In the mobile armature closed case, MMF is F0 and flux is phi1, which is the second condition of the magnetic circuit. Stored energy is A1 plus A2, the total. So this is the second condition. And change in the electrical energy results in change in the field energy in the magnetic loop and change in the mechanical energy. So as we follow from the equations, from the topmost to the second, change in the electrical energy is transformed to the magnetic circuit properties, integrating MMF from phi 0 to phi 1 results in an area, change in area in A1, okay? And if we follow accordingly, change in the mechanical energy can be graphically represented by A3 and A4 in this time in a fast motion. So this is the second, assuming flux is constant now, but MMF varies accordingly. Now, in normal motion, of course, both of them act together and there's no straight line trajectory following, rather very curved and complex and almost impossible to estimate accurately. But this is not our business. The results are important for us. So, if we consider the energy and core energy relationship on the top left characteristics, okay? Blue square box represents the maximum F maximum MMF maximum flux condition, and addition of energy and co-energy gives this value, or similarly, W prime or co-energy dependent on MMF and X equals to the total rectangular area minus energy of MMF and X together. So taking the differential of these two values, we can derive equations to find the mechanical force associated with this system. Now, the equations, both energy and co-energy, are two variable equations. Either they are these two variables are either MMF and X variable or flux and X variable. So let's start with the first one. In the middle, you see a box equation. Differential of co-energy equals to the flux times dF plus F field times dx. This comes from actually the partial differentiation or the total differential equation underneath, okay? So actually, flux is, okay, the partial derivative of MMF with respect to co-energy, and the mechanical force equals to the partial differential equation or partial differentiation of co-energy with respect to x. So our first equation of the force associated with this system, plunger system or anything, is partial differential of uh, co-energy W field with respect to x, which is seen in a red box at the bottom of the slide. So this is our first choice to calculate the force if we can calculate the coherent energy relationship between system or magnetic circuit MMF with respect to X. Similarly, if we use the complementary part or the energy relationship and take the total differential with respect to phi and X, this time the field energy is a function of flux and X, and the total derivative has two terms. As shown with the blue arrows and encircled variables, we have two equations of MMF, which is the partial derivative of the energy with respect to flux, and we have an equation of the field force, which is a partial derivative of field energy with respect to X. So this is our second alternative tool to calculate the force. As long as we are consistent, these two forces will be equal. This time, if we use partial derivative of x, partial derivative of energy of the field with respect to x with a minus sign in front, it's not seen very clearly, but at the bottom of the slide, force equation has a minus sign in front. So this is our equation with handwriting. We can use this equation as well. So we have two alternatives. We can calculate the same mechanical force either taking the partial derivative of co-energy with respect to x, or taking the minus of partial derivative of energy relationship or function with respect to x. These mathematical tools will help you to calculate linear mechanical energy conversions. Linear means along a line. In the next lecture, it's rotation. Equations as well as torque will be handled. So for linear case, any linear moment, linear forces, plungers, etc., we may use these two alternative methods. If we calculate, or if we can calculate the co-energy, then take the derivative with respect to x. If we can calculate the energy, again, taking the derivative with respect to x and minus sign in front, it gives the same field force as well. So if you look at the example 1 and try to solve this problem, there's a moving plunger in a, let's say, two-arm magnetic circuit. Center arm is energized with coil and current with the given parameters, and the moving plunger is shown with a smaller piece from left to right can move horizontally. And as you can imagine, if we energize the coil, the plunger will hit and close the air gap. So the question asks, derive an expression for the electromagnetic force produced by the electromagnetic device shown in the figure and plots a field against X. So initial gap length is C. So that's the maximum air gap condition, and I is constant during the motion, so that gives a clue to us. Constant I, which is the first assumption, Ni is constant or MMF is constant. So when MMF is constant, it's a slow motion. So it's better to use the co-energy relationship to calculate the F. So the solution is, of course, it's a summary of the solution. I just excluded a few steps in the solution, but you can follow and very easily fill the gaps. We start with the assumption. This is an idealistic device. Magnetic permeability is infinite, so reluctance of the core is 0. MMF is N times I, and also it's only exists that MMF across the air gap is important because the reluctance of the core is 0. So that MMF is Hg, which is the magnetic field intensity across the gap, times the distance of the air, so this C minus X. C is the maximum length, as you know, and the magnetic flux in this magnetic field is total MMF over the reluctance, that reluctance of the air gap. So the reluctance is just the length over mu0, that's an air, and times the cross-sectional of the gap, which gives mu0 Ag, A sub G, H sub G. Note that flux is variable because H times C is not constant during the motion, but that's a very simple expression. So the co-energy is, since this is an air, it's a linear system, 1 over 2 times F times flux. F is the MMF. And if we substitute the variables and continue and calculate the field force by taking the partial derivative of co-energy with respect to X, gives us minus mu0 A sub G Hg square over 2. Now Hg square, okay, apart from Hg square, everything's constant. But Hg square can be calculated from the first equation on the slide on top. Underneath, it's written with nice formula variables. If we substitute Hg equals to MMF over C minus X, then my field force is some constant times N square I square over C minus C minus X squared. Similarly, there's another problem. So finally, about the previous one, if we want to plot this force as a function, that's a kind of paraboloid, actually inverse square characteristics with which you can easily draw its diagram. In the second example, there's an iron slab with the upper part, let's say opposite U part is fixed, but underneath the big iron slab of mass capital N can move with 2 air gaps this time. Only you do multiply with 2 everything. The solution is not explicitly stated, but hint to calculate the force associated with this. Since phi is constant, it's better to use energy relationship. Take the minus of the partial derivative of energy of the system with respect to x. And in part C, AC force excitation also can be done accordingly. This is another solved example which you can self-study and learn, and also this example continues. This was an example from previous years, which you can self-study and practice your improvements or developments by yourself. Also, it's suggested to watch Chapter 3, Part 1 movie at Start Site under the Documents lab to see other approaches about the solutions of the previous problems. So thanks for watching my video, and I would like to have your contributions via email about anything. Thanks. Bye-bye.